Welcome to Streamline. My name is Kyle Bartholomew, Senior Metallurgist, Metcom Technologies. In this short video, I'll introduce Streamline and give an overview of its purpose. I'll describe how Streamline integrates into the Metcom grinding process management system, and I'll wrap up with an overview of the technical workings of Streamline's mill model, cyclone model, and pumping system model. Streamline was developed as a way to more precisely quantify the result of circuit changes made to improve classification system efficiency. Historically, the Metcom system has used heuristics, or rules of thumb, to estimate improvements resulting from things like improving cyclone water balance or increasing circulating load ratio. These heuristics were developed by industry experts and are the foundation of Metcom Module 18, Evaluation of Circuit Classification. While these rules of thumb are still useful, with Streamline, we can now improve the fidelity of our estimates through computer modeling. Computer-based grinding circuit modeling is nothing new in the minerals industry, and there are a variety of commercial and academic programs available. However, it is our belief that most of these models are so complex that it would be the rare practicing metallurgist who would have the time and inclination to fully understand their inner workings, no less put them to use for actual plant improvements. Existing models also rely on parameters that are not measurable in the field and assumptions that cannot be verified through experiment. Streamline is designed to be the practicing metallurgist's grinding circuit modeling program. Simple to use and understand, it is fully supported by Metcom training and tutorials. Streamline is the only grinding circuit modeling program built around the functional performance equation, and that uses classification system efficiency as the optimization metric. A step-by-step procedure replaces the trial and error method of circuit optimization often used in other modeling approaches. This saves time and effort, allowing you to achieve circuit improvements faster than ever. Finally, practical constraints such as pumping capacity are often overlooked in other models. These constraints are addressed in the Streamline application and overall Metcom approach to grinding circuit improvement. This way, you won't be caught off guard trying to do something the computer says is possible, but that physical plant equipment can't achieve. For those of you who have already completed the prerequisite Metcom modules, you'll see a lot of familiar worksheets, sketches, and calculations embedded within Streamline. For those of you new to Metcom, please understand that Streamline needs to be used in the context of the training program. You will need to understand things like cyclone separation performance curves, slurry pumping, and classification system efficiency to fully utilize the power of Streamline. Without this training background, it would be easy to misuse Streamline, potentially wasting a lot of time, effort, and money, and not achieving the plant performance you desire. The Metcom approach to grinding circuit improvement is systematic and based on time-tested fundamentals. Following the steps outlined in the training program will be key to your success. Now that we've covered the introduction and purpose of Streamline, I'll dive into the technical description of the math models used in Streamline. Streamline uses three fundamental process models: a ball mill model, a hydrocyclone model, and a pumping system model. At the heart of the Streamline application is the Finch-McIver ball mill model. This model was developed by Rob McIver and Professor Jim Finch at McGill University, and it mathematically calculates the mill discharge size distribution from three inputs: the ball mill feed size distribution, the ball mill feed rate in dry tons per hour, and the ball mill power draw. The Finch-McIver ball mill model is a first-order exponential decay equation that uses cumulative grinding rates to predict the output from the inputs. There are no assumptions made about breakage and selection parameters. The cumulative grinding rates are measured in your plant from survey data. Here's what the equation looks like. The cumulative percent of material closer than size I in the mill discharge equals the cumulative percent of material coarser than size I in the mill feed times E to the power minus K times T. From survey data, we know that the cumulative percent coarser than size I in the mill feed and discharge. T is the specific energy per pass in the mill. This is the mill kilowatts at the pinion divided by the dry tons per hour flowing through the mill during the survey. Note, for simplicity, this model assumes plug flow. No special residence time distributions are required to be measured or assumed. K, the cumulative grinding rate at size I, is the only unknown in the equation, so we solve for it. We do the same for all size classes used in processing the survey samples. Let's look at a numeric example to explain further. For this example, let's look at the cumulative grinding rate through 212 microns. The equation is shown at the top of the slide. From survey data, the mill power was 1,215 kilowatts at the pinion. Circuit feed rate was 192 metric tons per hour, and the circulating load ratio was 346%. This means that 664 metric tons per hour of dry solids were flowing through the ball mill. Dividing 1215 by 664, we get 1.83 kilowatt hours per metric ton for the value of T. From the survey samples, we measured 49.4% plus 212 micron in the mill discharge and 63.8% plus 212 microns in the mill feed. Plugging these values into the equation, we can solve for K, which in this case turns out to be 0.139. Interestingly, this is the same value for the mill grinding rate calculated by the functional performance equation. Please see Module 5 for more details. Repeating the calculation at all size classes results in the cumulative grinding rate curve shown here. The K values are held constant in the Streamline model. Changes to mill power, tonnage, and mill feed size distribution can then be put back into the equation with the measured plant K values to calculate the new ball mill discharge size distribution that results from changes to the classification system. Next, I'll go through the details of the cyclone model. In Streamline, the cyclones are modeled in a direct but effective manner. Simply put, the measured size-by-size recovery to underflow, as you learned in Module 7, is the cyclone model of the existing circuit. Streamline models the circuit at discrete values, as measured in the plant, and does not use continuous curve fit functions. Changes to the cyclone are modeled by shifting these discrete points left or right on the size-by-size recovery to underflow curve. Historically, we did this by hand by placing a piece of transparency over the top of a hand-plotted cyclone recovery curve, copying the values onto the transparency, then physically shifting it left or right to adjust the cut size. Streamline now does this same function, but mathematically. There are also tools within Streamline to assist the user in defining the cyclone separation curve of their choice. For example, if you know how much better your selectivity index will be for your new cyclone installation, the measured cyclone recovery curve can be rotated mathematically in Streamline to achieve this new sharper separation. But at its core, like all models, Streamline depends on good input data and good engineering judgment of the user to ensure that the model selected is something that can be achieved in practice. Next, I'll go over Streamline's pumping system model. The cyclone feed pump system is modeled using the Bernoulli equation, the pump power draw equation, and the manufacturer's pump curve, just as you learned in Module 9, slurry pumping. Recall that the Bernoulli equation defines the pumping system in terms of total dynamic head, which is composed of 4 subcomponents: static pressure, velocity head, lift, and friction loss. Static pressure is initially defined by the cyclone feed pressure measured during the survey, Later on, when you're making adjustments to the pumps and cyclones, static pressure will be adjusted based on the equations you learned in Module 8, hydrocyclone adjustments. You learned about velocity head in Module 9. This is the kinetic energy the pump imparts on the slurry as it accelerates from the sump into a moving flow in the slurry pipe. Velocity head is modeled in Streamline just as it is in Module 9. The velocity tables from the module are built into Streamline, which automates the lookup task for a majority of the cases. Lift head is calculated based on measurements you make in the plant and are put into Streamline. Finally, friction head is based on the same methods taught in Module 9, accounting for pipeline losses and losses created by valves and fittings. Total dynamic head is coupled with the pump power draw equation from Module 9 to estimate pump motor demand. The user still has to read their own pump curve manually, but detailed instructions are provided in the module on how to do this. Finally, when sizing and selecting the new cyclones in Streamline, the pressure, flow, and vortex finder relationships taught in Module 8 are used to estimate the new cyclone feed pressure needed for the application. Streamline is unique in the industry in its incorporation of the detailed pumping system calculations, which are vital to making the modeled improvements a reality in the plant. This concludes the video, Streamline Introduction and Model Overview. Details about how to get started with Streamline, how to use the models, how they interact, are provided in other videos in your Streamline account. Please review these videos and see the frequently asked questions in the technical support section of your Streamline account. Thank you for your attention, and again, welcome to Streamline.